Hi everyone, welcome back to another video about Python, and in this video we will use Python together with the library scipy in order to solve ordinary differential equations with boundary conditions, which is different from the previous videos where we use also Python, also scipy, but we were solving the ODE or the ordinary differential equations with initial conditions. In this video, we will solve ODE with boundary conditions. So what is the difference? Before going into some coding, I want to explain the concept. So that's my style. So a general concept would be we have a physical problem, and when we have a physical problem, we will formulate it into some mathematical formulas based on some physical principles or physical theorem. And after the physical theorem, we obtain some abstracted mathematical formulas describing our physical problem. Then also we will be given some information in order to solve our mathematical problem. And the information that's going to be given to us will be in either two forms. The first form is the initial conditions, which is you already seen in the previous videos, and the other form is the boundary condition. Just assume that this physical problem has one solution only, and the people who want us to find this solution of that physical problem can either give us the initial condition or the boundary conditions based on their preference, but we have to come up with the same solution. And last time they gave us the initial conditions in order to derive the solution, but this time they will give us the equivalent boundary conditions of that solution in order for us to find the solution ourselves. So this is the example of the concept. So the physical problem would be find the position of a vertical thrown ball, and that position will be the function of time called yt. And based on our physics principles and some physical phenomena that we learned in high school or university, we derive that the second differential equations, if you derive the position y, if you derive the position y twice in respect to time, then we will have the minus of gravitational acceleration for the vertical thrown ball. To know more about this derivation, please refer to any textbook, physical textbook, or any physics textbook, and you will find the formula derivation. But here we only use the formula in order to make the example, in order to apply the method to demonstrate how to solve the ordinary differential equations with boundary condition. And with the given information input, if we were given with the initial condition, which we can use the scipy solve IVP input in the initial conditions, then we can find out our solution yt, which gonna be satisfy this ordinary differential equation and also satisfy the given initial conditions. That was for the previous videos. In this video, we will focus on this branch, the boundary conditions. So just assume that this is the, if we have this kind of condition or we have the initial condition, the solution we come up with for the problem will be the same. So instead of having the initial conditions, we have the boundary conditions. And the boundary conditions means, because our solution is the function yt, and the boundary would be if we have the thrown ball will start at time equals 0 and it ends at time equal 10 seconds. and they give us the battery as the position at time equals 0 will be equal to the position of the ball at the time equal 10, and both of them are on the ground, or they both have 0 height. So you can see the difference. Here we have, when we have the initial conditions for the second derivative differential equations, then because it's second derivative, we need to have the 0 derivative, which is the function itself, and the first derivative when we are dealing with the initial conditions. However, on the boundary condition, we only have the value of the function itself. There's no value, there's no information about the first derivative of the function, only the information related to the function itself and on the boundary. Why is it on the boundary? Because we say we are finding the solution yt for the thrown ball from time equals 0 to time equal 10 seconds. So the boundary is when time equals 0 and time equal 10 seconds. And we just need to know about where is the position at that boundary. And from that, we will have to find out our solution yt in order to satisfy this formula of the physics problem and also satisfy the boundary conditions. And this is what we are dealing with in this video. As a summary, the problem that we are going to solve in this video as an example will be, we have a ball thrown in a vertical direction, and that thrown ball will be described by the second derivatives given here. On the other hand, we will have some boundary condition for the vertical thrown ball, which is at time equals 0, our function equal to the position of time equal 10 seconds, and both of them have the 0 height, which means in our case will be the ball on the ground. And we need to find the function yt describing the position of the thrown ball as a function of time, which is the solution to satisfy our derivative equation and also the boundary condition. So now let's go to the solution to the problem of solving the ordinary differential equation with boundary condition. In this case, we'll use a technique named shooting method. To know more about the description of this method or this technique, please refer to the book, the reference book that I put in my description section of the video. But to sum up, the technique requires two important steps. So the first step is that, so you can see for the boundary condition, even though we have the second derivative, but the information only relates to the the 0 derivative. There's no information about the first derivative. If you remember in the previous video, in order to solve our second derivative, we will need to have the 0 derivative, which is the function itself, and also the first derivative. But on this case, we only have the 0 derivative, so we lack the first derivative. So our first step will be find out the first derivative value at time equals 0. With the first derivative solution, we also can obtain the position satisfying our boundary condition. We need to find the missing initial condition of our boundary condition. And when we can find out the missing initial condition, which is the first derivative at time equals 0, we can just plug it in again, and we use solve IVP, and we find out our solution yt. That's the second step. It means with the shooting method, we will transform our boundary condition to the equivalent initial condition. And when we have the equivalent initial condition, we again just use to solve IVP and obtain our final solution for our differential equation. So in summary, the shooting method somehow involves two steps. The first step is that we need to transform our boundary condition to the initial condition. And in order to transform from the boundary condition to the initial condition, we just need to find out the equivalent missing derivatives information of our boundary condition. And because we are dealing with the second derivative and we already given with the zero derivative, so the missing derivative is the first derivative at time equals 0. And if we can find out about that missing first derivative information at time equals 0, we can transform our boundary condition into the initial condition. And after the transformation step, we go to the second step, which is just solving a ordinary differential equation with a normally initial condition by using the scipy solve IVP, and we will obtain our solution, YT in this case. And now this is just some idea for the first step. So our first step is to find out the equivalent initial condition of the boundary condition. And the equivalent initial condition of the boundary condition would be find out the first derivative at time equals 0. What will be that value in order to make our function satisfy the boundary condition given to us? So here I describe a system. The input will be like what will be the value of the first derivative at time equals 0 into our system, and then the output of our system will be the position at time equal 10 seconds will be 0. So that's our system that we need to solve, right? But you can easily somehow link it to a very simple function. For example, our input here looks quite complicated, but if we like somehow simplify it into like input of a variable x, and our system be simplified like for example a function like this, like fx equal 1 plus 0, and the output is where our fx equals 0. It means the x that we want to find at the input is the root of our function, right? Because we need to find the x where our fx is equal 0. So if you can somehow link that concept to our system to solve the problem, we can say like, okay, this is the input to our system, and the output of our system is something equal to 0. It means we can somehow think that our input is the root of the system to have the output equal 0. So generalize of this idea would be finding the root of this system. The same with a very simple case where we need to find the root x of a function fx. And if you remember earlier, we also using some scipy.optimize. In this case, I use scipy.optimize.newton to find the root of the function. So I also can use this scipy.optimize.newton to find the root of our system. And in our case, the root of our system will be a value of the initial condition where it satisfies our boundary condition. You got it, right? I hope you got it. So the first step is to using this scipy.optimize.newton in order to find out the root of this system. But how can we describe such a complex system in general, in our case? So our system, of course, have to satisfy the ordinary differential equations of our physics problem, and is described by the second order derivative. And our system is a second order derivative. It accepts an input of the first derivative, and also there will be some additional input, like the value of the function of the zero derivative. The system is a ordinary differential equation, receives information of its initial condition and output the solution, and from the solution we can extract one value from the solution and make sure that it equal to 0. Somehow we can see a pattern. It looks the same like how we solve our normal differential equation using the scipy.integrate solve IVP in the previous video. So our system in this case will be described by the scipy.integrate solve IVP. And when we describe our system at a scipy.integrate solve IVP, we receive an input of the first derivative, and then we have an output. And if this output is not equal to 0, then with the scipy.optimize.newton, the function will automatically iterate to another input, another value of the first derivative at time equals 0, and input to our system. And it checks the output at this value. If it's not equal to 0, this optimize.newton again iterate to another input, another value of our first derivative at time equal to 0 into our system, and then check the output. If it's not equal to 0 again, then optimize.newton function will continue to iterate to another values of our first derivative at time equals 0 until it satisfies the condition of the output at our position at time equal 10 seconds equal to 0. That's it. And for the system, it doesn't change because the system itself will be described by the scipy.integrate solve IVP. With the scipy.integrate solve IVP, we can just receive any input and we can output a function of the position according to time. And after the first step, when we obtain the satisfied first derivative at 10 equal to 0, in order to have our position at time equal 10 equal to 0, then we already transform our boundary condition into the initial condition. So the second step is just normally solve on the initial conditions, and then we find out our solution yt. And that's the end of the concept. Now let's go to the code. And here's the code in Google Colab that I already prepared, and you can find out the link to this code in the description section of the video. So first we need to import our necessary libraries, which is NumPy, SciPy, and the matplot, in order to plot our solution to see how it looks like. What is our aim? Our aim is to find the position as a function of time of a vertical thrown ball, which is described by the ordinary differential equation and has the boundary condition at which the position at time equal to 0 and time equal to 10 seconds on the ground, or they have the height of 0. So our first step is to find the equivalent initial condition at time equals 0 of our position function. If you remember, I also put the concept here again. We need to describe first the system, and that system will be the described function input to our scipy.optimize.newton. So the system will be a function where we have to use the scipy.integrate solve IVP. So that's how we describe it. if you don't know how I do this description of the system in order to input to our scipy solve IVP, please refer to my previous video about the ODE with initial conditions. I explain everything, but here I just apply the concept again without any further explanation. Because our system is described by the ODE and we somehow need to obtain the position based on a guessed initial input, a guessed first derivative input. So we describe our function based on the ODE of the second derivative, and we return the solution to that system. And you can see this is where we define our system. We input the system and then we input the interval of time from 0 to 10 according to our problem, and the initial values of course will be the guess position at time equal to 0 and the guess initial first derivative at time equal to 0. So you can even see it here. The initial is 0 and the guess for the first derivative, of course at the beginning we have to input 0, but after that the function optimize.newton will start to iterate from 0 and find another first derivative at time equal to 0 in order to obtain a solution, and the solution at which we can have our position at time equal to 10 seconds. This is position at time equal to 10 seconds. Minus 1 means I extract the last value in our position function, because our position function here is a function, so it contains a lot of value, and we just need to check the boundary condition, which is the time at 10 seconds of our position should be equal to 0. So that will be the function we input to our optimize.newton, and then we input our initial guess of the first derivative, which after that will be iterated by the optimized Newton to find out what will be the appropriate value of the first derivative to obtain our boundary condition equal to 0. And the tolerance, the lower the tolerance, the better we're gonna have for our solution. And max iter is the maximum number of iteration that the optimized Newton will start to iterate from 0 to our appropriate solution. So let's define our system here, and after define our system we need to define the function to solve with our optimized Newton. If you don't understand what is the function input to the optimized Newton, please also refer to my previous video about solving nonlinear equation using optimize.newton. In this case, I will just demonstrate the concept, and here we obtain our solution. So this solution is the first derivative. This solution is the first derivative of our position at time equal to 0, satisfying the boundary condition given to us. So the first step is done. We already successfully transformed the boundary conditions into the initial condition. Now we have everything for solving our function as a differential equation with initial condition. So we only need to put our differential equation here, which is we already described, together with the interval, of course, from time equal to 0 to 10, and put our solution for the first derivative, which satisfies the boundary condition. With the solve IVP, we will have the final solution for our position according to time. And now if I plot it, this is what we obtain. This is our time and this is the height. So at time equal to 0, we are at the height of 0 meter. and at time equal to 10 seconds, we also obtain the height as 0 meter. So that's the end of solving ordinary differential equations with boundary condition. And I hope that somehow the video is useful in a way. And if you have any feedback, please give me the comment. If you find out anything wrong, please also give me a comment. And don't forget to refer to the book in the reference in the description section of the video to know more the description of the shooting method. And thank you for watching. See you in another video.